Welcome to the second video on combined stress. In this one, we're going to determine, we're going to go through the four equations that we need to think about when determining the stress, and we're going to start setting up the equations specifically for our problem. Now that we have the attributes of the cross-section determined and the forces and moments at points A and B, or rather at the cross-section that they share, we can now move on to determining, starting to figure out the stresses at these points. Now, there's generally going to be four equations that you're going to want to consider. You're going to want to consider your normal stress from normal applications, which is to say the equation P over A, that good old equation. We are also going to want to consider the normal stress from bending, which will be equal to moment times your distance from the neutral axis, which will be a different axis for your different bending directions, divided by your second moment of inertia. Now those are going to be what gives you your normal stresses. You're also going to have to consider, let me just draw a line right there, the shear stress. So you're going to have shear stress from transverse shear, and that will be V times Q divided by your second moment of inertia and the thickness of the section at that point. And there's also going to be shear from torsion, and that's going to be equal to the torque applied times your radius, or how far you are from the point, divided by your second moment, or sorry, your polar moment J. So you're going to need to consider all four of these equations in order for you to determine the stress at any given point. Let's determine what these are so that we can simplify them when we plug in our values for where A is and where B is. So let's start with the normal stress caused by an axial load. That'll be very easy because it results in a uniform distribution of load. It's going to be the load over the cross-sectional area, which this is going to be 1,200 pounds, and we said that we would be dividing that by pi, basically. Pi square inches. And that's going to give us put an equal sign in there, 381.97 psi, and that is going to be uniform in its distribution. So we don't have to worry about where something is in order to just pop in that for the stress. You see it's a constant. There's no values that we've left unfigured out for this one. Now, for the other ones, they're going to be a function of the location of A and B. So let's look at A first. And let's look at the moment at A. So, From now on, this is for point A. I'm going to do point A, specifically things, in green. So, we're going to have stress due to bending about both the y-axis and the z-axis, which now you can't see because I've slid it up. Okay, so we've got that as an issue. However, at A, y is equal to 1, and z is equal to 0. So when we set up our normal stress for a moment about the z-axis, moment about this axis, we're going to have that the normal stress it's going to induce is going to be in the x direction. And it's going to be equal to the moment times y over I, which in this case is going to be negative 3,600 pound-inches, because it's the moment about the z-axis, divided by what our second moment of inertia was, which is 0.785 inches to the fourth times y. And that's going to be, we can simplify that, negative 4,586 as pounds per inches cubed, I guess, times y. And then we'll also have, and this isn't specifically for point A, right? This holds for any point as we move up and down y. But if we plug in 1, we do get the value for A. The normal stress in the x direction due to the moment about the y-axis is going to be the moment times about the y-axis times your distance in the z direction divided by the second moment of inertia, and that's going to give 2,400 pound-inches divided by 0.785. This one, is times z, and that's going to equal 357.3 pounds per inches cubed times z. So at point A, we're going to have normal stress from the axial load, which acts uniformly, and we're going to have some normal stress from bending about the z-axis. Right, we're bending about this axis, that means this top part is going to be getting shorter and this bottom part is going to be getting longer. It's from this force, right? So if we force this up, this is going to bend. We're not going to get any stress at A due to this force right here, because we're going to be bending about the y-axis, so that's going to be forcing it this way. That's hard to do. So y is at the A is at the neutral axis for that, so it's not going to induce any stress at all. So that's the normal stress at point A will be the sum of this and this with 1 inch applied right here, because that's the point where A is. It's a 1 inch radius. Let's move on to looking at the shear equations.